All right. Welcome everyone to this, everyone who's in person and as well as online, to a series of software development presentations. We are fortunate and grateful to have some experts from Kitware today to present on web frameworks, visualization frameworks. Just a few weeks ago, some developers there gave a presentation on parallel algorithms and multi-threading, which is very informative and interesting. And so we're grateful to have them. Today, we're going to try to leave some time at the end for questions, although I think after Matt's presentation, if I understand, you need to leave a little earlier, so maybe have some questions after that. And maybe I'll just leave it up to each individual presenter whether you want to hold questions to the end or whether you're okay with having interrupting questions, and I'll watch for like chat questions online as well and maybe offer some of those. And I'll just should I introduce everyone, or I guess we can just have maybe introductions as we go. And I believe Matt McCormick, you are the first to go.
Yes, thank you, Gene. And yes, I will have to leave, unfortunately, a little early, but would love to discuss a few questions after our first presentation here. So my name is Matt McCormick. I am an engineer here at Kitware, and I'd like to discuss and share with you one tool for web-based visualization we have at Kitware called itkwidgets, which are interactive widgets to visualize images, point sets, and 3D geometry on the web. I'd like to start off by thanking everyone there at SCI and at Utah. We've been working together with Jess Tate and Rob McLeod and Chris Johnson and also the people I've been working with at Kitware here, Will Schroeder and John Christophilian Robin. We've had a wonderful collaboration together supported by this grant from the NIH. And the motivation for these web-based visualization tools are multifold. So first, we think about when we're doing research software development, where are our research components located? And if we're doing medical or biological imaging, our data might be at the imaging acquisition system, like on a CT scanner, or the data might be collected in a research lab on a laboratory workstation, or maybe a cloud computing cluster like AWS, or an HPC cluster, traditional cluster. But more recently, a researcher who's trying to understand this data wants to work with it, but it's getting larger and larger and it's located in these systems. So the ideal situation is that we can access that data through the browser and gain insights through visualization. And this is more important with COVID. And when you're also in remote locations, like here, I'm in sunny North Carolina, we want to take advantage of the sunshine and get to that remote data at the beach, or in Utah. If you're out on the slopes, you want to access the data remotely. So the web is a great way to work with data sets remotely. It's a great way to work with large data sets because the data can be in situ with the compute resources that you have to work with. And the other main motivation for these web-based tools is that they require zero installation. So it's much easier to do the type of computing and visualization that we're interested in doing. And so what are the ITK widgets? They are interactive widgets to visualize images, point sets, and 3D geometry on the web. Here are a few examples of what you can do with it. On the left, we have a mouse brain, the CCF Atlas. On the center, we have a CT of a tooth. On the right, another CT of a knee. And if you want more information, there are documentation at itkwidgets.readthedocs.io. And what is special and unique about ITK widgets is that it has some of the cutting edge cinematic volume rendering support that we've been integrating into V2K.js at Kitware enabled. And it has support for working with a lot of the AI tooling that's out there. So PyTorch or TensorFlow in Python in the medical imaging space. There's a set of software called Munai. And you can use these interactive widgets in the browser with common frameworks you're used to, like Jupyter Notebooks, Jupyter Lab, Jupyter Lite, which is client-side Jupyter, Google Colab. There's a AI system for the cloud called SageMaker coming from Amazon. We're working with them to get support there. And also there's in progress support to have standalone Python applications. So what does the visualization look like? So you can have these volumetric renderings supported by VTK.js and interactively work with them and generate them. Select regions of interest, change your visualization parameters, your color maps, your opacity transfer functions interactively with client-side widgets and tools for changing the visualization parameters, slicing volumetric data, working with label images on top of the intensity images. So this might be the output of a deep learning convolutional neural network segmentation pipeline, and we can do some rendering of the different labels on top of the underlying data. We can also work with meshes or geometry, getting that understanding of cows or horses as their skeletons or surfaces, and point set data sets, understanding maybe statistical distributions or working with data sets like LiDAR. And then all of these data sets together, whether you're processing and working with them in the visualization toolkit VTK or ITK in Python or any other Python-based tools. You can look at the results together. And how does this work? So it's based on some core technologies that can be extended and applied in different contexts. So these core technologies are ITK WASM, WebAssembly, so analysis and visualization in WebAssembly, running either client-side or compatibility with server-side and Python interfaces. Our core rendering front end is VTK.js, so visualization toolkit built for client-side rendering in JavaScript and WebGL. And the way we communicate through these different contexts is a peer-to-peer communication protocol system called Enjoy. And that's how we talk to different contexts in the browser or remotely on the server. And another core technology that this is built on is ZAR, which is a multidimensional array format in memory on disk that works with chunking the data and highly compressing it in a highly compressible way in many different stores, web-based stores, and instead with working with data, streaming it on the web. And you can access it on different contexts like Jupyter, as we see in these illustrations in the center. And then if you want to scale the client-side processing, there's native support for Python-based distributed computing library called Dask, and integrations with standard tools you'll see in the scientific computing system in Python, NumPy-based tools, machine learning-based tools, and then apply it in different contexts like Jupyter, as we were talking before, or Google Colab, Amazon SageMaker, or Jupyter Lite. So when you're working with the data, it can work pure client side, so running just in your web browser. And in that case, you can access remote data sets. They may be very large data sets stored remotely, larger than would be stored in memory, can be stored in memory or rendered in memory on your local system. In many cases, those could be this ZAR-based format, or you can have data that is like a stack of TIFFs or PNGs and load them from your local computer, and they'll be processed and built into the same sort of data model and rendered locally with WebAssembly. And the same infrastructure and APIs are used for working with remote data sets that are either talking remotely through this ImageRay library or through Python based processing and sent remotely to the client. And it can be used as is what you get, or it can be customized, and you can build custom front ends in your client-side front-end framework, graphical interface framework of preference. Vanilla HTML or Vue.js is a common framework, or React.js is another common framework to completely customize the UI, or maybe just implement the features that are relevant for your system that you'd like to integrate it into, and integrate it into something that's a custom application. So as a component, really, of a custom application. So what we're seeing in this slide here in the upper right are two user interfaces. They look quite the same. They provide the same functionality, but they're implemented in different front ends. On the left is vanilla HTML, and on the right is React.js. And below we see an example of the system being integrated into a custom application where we have a tool built for assisting developers that are creating new AI pipelines. So there's a popular visualization tool for developing AI pipelines called TensorBoard. And this brings in 3D visualization capabilities into TensorBoard, but you see it integrates nicely into the TensorBoard UI system that's built in React and Material UI. And we're working on server-side rendering. So you can do server-side rendering with, for example, 3D Slicer or other tools out there, such as those developed at SCI. And what we're seeing here is open source, and we welcome contributions and extensions, and love to see what you can do it. Here's where you can find the source code. And here's also where you can reproduce the slides that were presented today. So some of the data sets that you sent here, I'll put a link into the chat for this presentation if you have access to the chat here. But you'll see serverless client-side rendering. This is a brain imaging data set of a very high resolution MRI brainstem. And here, this is kind of real-time interactively loading, progressively loading this remote data that's highly compressed as it's coming through. And there's similar data sets here of, we're getting more and more data there as it comes through progressively. And we also have a Jupyter example, or an example of loading the application that you can load local data from your system. So thank you for your time and attention. I'd be happy to answer any questions or have a discussion more.
I got a quick comment. If you go back to your first slide.
Are you able, here, let's, ready to catch this?
Anything with this? Just speak into it. Just a quick comment. Yeah, that one right there. Go back.
This one. Okay.
It's cropped, but if you go back online, not that one, the one before,
Yeah.
that one. If you go online and you find that picture, and I can send it to you, in the upper right-hand corner is going to be a phone number. And that phone number is area code 801, which is Utah. And then the next 3 digits are 581, which is the University of Utah phone number. And then above that phone number is the name Hearn, which was Tony Hearn, who was working on computer algebra. So Feynman was literally calling Tony Hearn here at the University of Utah to do Feynman diagrams.
That's brilliant. I love that. Thank you for sharing that. I will have to look for that.
Yeah.
That
And
phone
also I'll
number.
send you one if you need it, but I've got one right here.
If I call that number, will I get anybody? No,
Here's the funny thing. It still rings into the physics department. I've called it. And I don't know whose phone number it is, but it's an active University of Utah phone number in the physics department.
Very nice.
Too loud. Anybody else have questions? Is there any online?
No, I don't see any chance.
Jack?
I have a question, yeah, sure. Hey, thanks for the presentation. It's really good. I just had a quick question about what's next for ITK widgets. This is all really, really interesting and exciting, but like where are the next points of development for you guys?
That's a great question. Yeah, I think more of this support for client-side rendering or I haven't seen remote rendering, and also making this customization easier and better documented on how to build these custom applications with it. I think also, reaching out and making it easier for people who come from a background of maybe just C++ and learning how to work with these web technologies, I think is important.
Cool, thanks.
Okay, I have a hopefully mostly quick question. So for the remote rendering, you said that the data was rendered remotely, but the compressed data was sent over the server. So how much load does the local client have to do to visualize the compressed data? Is that customizable or?
Yeah, the load is lower in that case because you're just sending the rendered 2D image. Yeah.
And in the 2D image for each frame.
Yes. Yes.
Oh, cool.
Yes.
And so the frame rate is mostly dependent on the connection speed, I guess.
Exactly. Yes.
Okay. And one more quick question. I guess maybe these will at the end there might be, but we'd like to know where we want to know where all the tutorials and examples are that we can use to learn.
Yes. Great question. So this is the place to go for more information. Sorry. Is the Sphinx documentation located at the bottom of this slide here? Read the docs.
Okay, thanks, Matt. I'm getting a message that we need to continue. So I don't know if it's Sebastian or Forrest or who's next.
I think from the list, I think I was next. So I'm just going to go ahead and hopefully see you. Sorry, I put it on my wrong screen, so I won't look at you if. Okay, here it is. So the reason why I'm here today is basically to talk and introduce Tram for building analytical workflow fast and simply. I try to be as brief as possible. There's plenty of material online for you to look at and get great example, but I really want to nail down the nutshell of what it is and how it can help. And of course, thank you again for having us today. I think it's a great opportunity for all of us to share what we've been building and creating for university researchers and so on. So thanks again for having us. So what is Tram? So Tram, first of all, you can obviously get it from the web, but it's a Python framework that enables rapid creations of interactive analytical application with or without VTK preview. It was initially designed with 3D visualization in mind, but it definitely grew into something bigger in the sense that you can do AI, you can do 2D charts, mapping infrastructure, just by working with some Python magic and not necessarily knowing much about the web world to some extent. So technically what it means with Tram is creating a graphical application is no simple because all the logic, the UI definitions can be done in plain Python. And you will see a tiny example later on where just a single file of 30 lines of code give you a nice UI and an interactive environment. It's powerful because yes, we are based on Python, which means all the wrapping libraries, C++ tools, such as NumPy, Plotly, VTK, PairView are becoming accessible from that Python layer. So you can do crazy data visualization and data processing using Dask, like Matt was talking about before. Tram doesn't have any opinions on what you should use or should not use. You are in Python, you do whatever you want. And the nice thing also is the ubiquitous part, which means that once you've created that application in Python, can run on laptop, desktop, cluster, in the cloud, using remote rendering, local rendering, can even be integrated into Jupyter Notebook. You've got many ways of using that same web frontend to drive your applications. And how does it work? Well, if you want the big picture, basically you start with a Python file that is going to run on what we call the server side. Of course, if you're local on a local machine, your server is your machine is your server and your client at the same time. But technically, you will have some Python things running on the server side. And then what Tram is going to give you is some infrastructure for a shared state that is going to be synchronized between the web UI and your Python scripts, on which you can attach some reactivity infrastructure. So you can listen to modifications and react to it by executing functions. Then on top of that shared state, you've got mechanism for calling methods in both directions, meaning when you click a button, you can call a function on your Python side, or when you've got something happening on the Python side, you can call a functions in a component in your web UI, for instance, if it's like a JavaScript application, like the ITK widget that Matt is showing up. Technically, if it was exposed in Tram, it could be driven and like fed from the Python world by asking questions directly to that JavaScript world. And then finally, the Python will have to provide that view template or the HTML template of what the UI should look like, where you are going to insert your functions that needs to be bound to a button click or something like that. And on top of what you've got already available within Tram, you can expand it by adding additional UI module that will be pure JavaScript things that will be enabled and that can be driven and instantiated from your Python application on the left side in that slice. And that's basically gather the various degree of freedom we've got with Tram. Like we are really playing with those 4 concepts, and that's just about it, which make it very powerful in many ways. So maybe you might be wondering, but what does it mean in concrete world? Like, how does it work if I'm like a Python developer? Well, when you create a Tram application, the main goal that you will have to deal with is orchestrate your various component or logic of your application using any kind of Python library available to you. And then what Tram is going to give you is that 4 entry point where you have that state that is going to be able to drive the UI, or the UI will be able to drive the server side by exchanging that small object variable, the events mechanism for dealing with mouse interactions, for example, the widgets, which will be those graphical pieces that you're going to organize into a UI or a layout, another way of thinking of that. But that's basically what you get with Tram, those 4 big picture where you describe your layout, you place widgets into the space, and then you start binding things with your Python code through events and states. Once you've got that application, I mentioned before that there was like some ubiquitous deployments. Well, what you get is a Python command line interface where you can just run the command line that will open your browser, and then you can drive your data processing, visualization, whatever you are aiming to do or monitor. That can work locally. You can use that same application and expose that inside a cell in Jupyter that will still be reactive. So if you've got some UI with some sliders and so on, they could modify elements in your Jupyter namespace. Or you can even have another cell in the Jupyter that you are modifying that will affect maybe the 3D visualization that you have with one of your tram application inside Jupyter. Next, you've got the opportunity to create desktop application by just bundling that server and that client together into a double-click executable that can run and be deployed as a regular desktop application. And finally, you've got all the cloud world or HPC world where you're going to run your Python application somewhere else and just connect to it using your browser to drive what you are dealing with. But the neat thing about that is you're not changing anything in your code base. Like all of that became available out of the box, but you just write once, and then it's up to you to bundle it or expose it in a different manner. This is a simple example. Of course, I made a typo. That's why there's a big VTK class underneath red things. I should have like snake case it. That was the correct syntax. But those 30 lines of code is actually the application we can see on the left. It's technically using pure VTK.js for doing the rendering, but we have mechanism to easily embed a render window of VTK, either saying, I want to do remote rendering or local rendering, or both, meaning that you can have like a toggle that will automatically switch by, I want to send images to my client because I don't want to move the data over there, or actually the data is not too bad, let's switch to local rendering, and then the geometry, the surface mesh or something will be sent to the client, and the rendering will happen locally. So with one line change of which view you want to instantiate based on the render window that you may have in VTK, you have the opportunity to switch between sending geometry or dealing with images and get like a nice way of interacting with your visualization. And of course, we have more, meaning that if you go on the tram website, there's a course, there's a video recording of a course that you can like just take the time to watch. It's free, there's no expense of that. There's a tutorial with exercise and example to go through. And on the left side, there's a couple of like examples showing some use cases of how to do things with various elements, such as Plotly, Matplotlib, VTK, PairView, and so on. So lots of material available to you. And here's the questions.
Nice. Thank you, Sebastian.
Sorry, I tried to be as fast as I could, but
No, that's great. That's right on time. Any questions here? We could also save them till the end as well. Yeah.
Clarifying questions.
I'm not seeing any here, or I just saw. No, nothing in the chat. Okay, so I guess if it's all right, we just move along with Forrest.
Yeah, sure.
Thank you.
Moment to get this screen sharing thing working. Meantime, which one is it? Which one is it screen sharing? I don't know which one is sharing.
That's
You can see your screen.
you can see your screen if you just go full screen. I think in the slides, that'd be slideshow.
Does this work?
Yeah. Yeah.
Okay, cool.
Yeah, looks great.
Hi all. I'm here to talk about VolView. I'm from the medical computing team here at Kitware and been working on this. This is a fairly new project, but we're pleased to have been able to finally release its initial version. And so I'll get to talk about it to all of you. So
what is VolView? VolView, in a nutshell, is an open source radiological viewer that resides completely in your browser. You don't need to have any server hosting I mean, you have to host the assets, but you don't need to have any special server or anything. It runs all self-contained in the browser. It provides fast and interactive visualizations of your medical data. So this is 3D, 2D, whatever you have. And because it's all in the browser, it is secure. There's really no, you load in your data and it doesn't necessarily go out and, get sent to any particular service or anything. And it's built on the tried and true technologies of VTK.js and ITK WASM, thanks to the work of Sebastian and Matt. It's also a customizable platform for whatever workflows you might have for your medical domain. And so just a couple of notable features that exist in VolView. We have cinematic volume rendering, which is a high quality, high fidelity rendering of your volumes. We have completely local DICOM loading. I'll touch upon all of these in later parts of this slide. We do various kinds of color presets for whether you're doing like MR, whether you're doing CT, whether you've got ultrasound, whether you've got X-rays. We have the capability to slice and dice your data to, maybe you need to visualize a particular section, maybe you want to annotate, maybe you want to paint a segmentation mask. And it is a fairly customizable application for whatever target you have. So just briefly going through some functionality, we do have support for annotations of various kinds. Right now, master, we only have measurements and segmentation masks, but we currently have a couple of other widgets pending, such as contouring. We have support for angle and bidimensional. That's not yet made it in, but we have it in a different application. Region of interest and like area measurements and pixel probes, and kind of like a good set of standard tools you might find in a radiological viewer. One of the neat aspects of VolView is that it supports native DICOM loading. And so you've got a bunch of DICOM files on your computer, just take them, drag them into the application, and it will sort and categorize the slices for you and give you a listing of your data sets. And so it's not, supposed to be like DICOM packs and, be able to sort, filter, query, and all sorts of things regarding DICOM, but it's meant to be a quick and easy way to be able to give you an overview and visualize any DICOM data sets that you may have residing on your local machine. And like I said, it's all local. Nothing gets sent to any sort of server. You have full control of your data. You can take VolView, you can disconnect your computer from the internet, and it'll still run just fine. Another really, really cool feature in VolView is we have realistic volume rendering. And so, like Matt had touched on, this is the cinematic volume rendering functionality that exists in VTK.js. And so you no longer really need to purchase licenses for high-end software that takes your medical data and tries to render it to be really, really photorealistic. You get that for free, and it runs all completely in your browser through VolView. And so you can get high quality visualizations of various parts of anatomy depending on your transfer function, and you get light controls. You get a bunch of customizable options for how you want to visualize your data sets in 3D. Finally, this is also a relatively new feature. We do have optional support for Python integration. And so what does that mean? Well, I've been talking about how VolView is all great and runs in the browser, no server. But suppose you want to run some like I don't know, you've got some segmentation algorithm, you've got some AI inference that drops biomarkers, and you want to do some diagnostic stuff or something. And so we actually do have support to integrate with Python servers, or really any servers for that matter, to load data sets, to run inference and algorithms on data sets and produce results. And it basically provides a means to customize VolView far beyond the constraints of the web browser. And so if you've got an algorithm, you want to see the results of, let's say, some classification given you painted a segmentation, then you can do that in VolView and with the Python server extensions. So I was going to do a demo. How are we on time? Because I figured, for VolView, this is an application. It's so much nicer to see something in action than talk about it. But I also want to be cognizant.
I think we still have 5 minutes.
Okay. In that case, I will briefly do a demo. This will be quick. I actually need to switch over to here.
Yeah, that's 5 minutes on yours, not 5 minutes on the whole. Sorry.
Okay.
I think you have time, yeah.
Okay, cool. Yeah, so this is a data set that I had just loaded up. We do have support for sample data sets. So, we can load up this cardiac cine, where you can see in this view, we've got the cine aspect of this MRI. And I'm going to switch back to this data set. This data set is probably the most interesting in terms of the cinematic volume rendering. And so you can, it's going to be kind of slow from Zoom, but we have various means of adjusting your visualization such that you can tune it to whatever quality you want. And of course, keep in mind, the higher quality, the slower the rendering will get. But in VolView, we strive for a balance in quality versus interactivity, because, well, we all know you want to look at your data sets, but we also want to make sure that it doesn't take forever to look at your data sets and have it look good at the same time. And so you can, of course, adjust color presets and the transfer function as necessary to highlight various aspects of your data set if the defaults aren't sufficient. We do have support for crosshairs for slicing and examining various bits of anatomy. We have support for labeling. So maybe if you wanted to, I don't know, label bits of, I guess, this and go down the line. And generally, you can use this to create and whatnot. And for instance, measurements also work for measuring various bits of anatomy. And then we also have support for cropping if you want to examine certain parts of your data set. And specifically in the 3D view, you can choose to crop, and then you'd be able to visualize basically your data that's been sliced. And so that's just kind of like a very quick overview of what VolView supports, and there will be more on the horizon. This is an application that's still very much in development. And I don't have a demo for the Python server today because that requires me to go and run it and attach it. But imagine, let's say there was a button that allowed you to take this segmentation mask that you drew and submit it to your server, and then have that do some inference and return, let's say, I don't know, a new segmentation mask that's been filled out, for instance. So it's only limited by your imagination in that regard. So I'm good. hop back to the slides. And find the slides. Wherever the slides are. Where did my slides go? Oh, here. Do you see this now?
Yes.
Okay, so I'll link this. I'll paste the link to these slides so you can actually play with it yourself. The application is freely available on the web, and you can load data sets, you can explore VolView and have fun with it. And we have links to the homepage, the documentation, as well as the repository. So thank you very much.
Thank you, Forrest. Any pressing questions? You can also leave those until the end.
I had one quick question, Forrest. What's the status of support of DICOM Web if you wanted to pull data directly from like a DICOM Web provider?
Oh, yeah. Thank you for reminding me about that. So VolView also supports optionally access to your DICOM Web dataset, DICOM Web servers. So if you've got an existing PAC server, let's say Orthink or something else, and it exposed DICOM Web, you can point VolView to it and it'll load up your data. You can browse it. It's not going to look pretty, but I mean, you can browse it and then you can load your data up.
Thanks.
And that was a fairly recent addition as well.
Okay, I don't see any other questions here. So Jean, if you want to go ahead.
Yep. Okay, you should be able to see my screen.
Yes.
Yep. Okay, great. Okay, this talk is a bit different from the other one. It's going to touch on all the aspects and focus on how to expose an existing desktop application and make it available for like Jupyter Web. And we're going to review the why we do that, how we do that, and etc. I'm going to skip that. Goal of the talk is to explain why integrating a traditional desktop application in Jupyter makes sense, and then describe how why it's useful in the context of the Jupyter ecosystem, and then present a specific use case that could be applied to other applications. To paraphrase, we're going to see the advantage of integration, what is Slicer briefly, and why it makes sense in that particular case. What are the Python capabilities of that desktop application and why it's relevant in the context of the integration. The specific of the SlicerJupyter kernel, and if time allow, a demo. Okay, problem statements. Let's say you have a desktop application that's fairly elaborated, and you would like to integrate that in a notebook. Is it possible to do that? And what if you found that there's already an existing application that allow you to implement this workflow, and you learn that the Jupyter environment provide a lot of tooling that you would like to reuse, and that is made possible through the SlicerJupyter extension that prevents you from redeveloping all the functionality from your desktop application. In that particular case, it's an extension of the Slicer desktop application that can be installed through like an app store built in the application, and then you can leverage all the existing functionality that you have been developing for years. And what are the advantages for the desktop application? You can remain relevant, and you can also run your desktop application remotely. And then it also exposes to the Jupyter ecosystem additional feature that wouldn't be available with more standard Python package. Now, what is really Slicer? Yeah, it's a desktop application that allows you to process images, embed DICOM, review 4D data set and whatnot. That's open source and also cross-platform. And yeah, what are the capabilities? DICOM capabilities, integration with AI pipeline, 4D data support, Python scripting, integration with AR and AR pipeline, and also integration with a broad set of Arbor for surgical guidance and whatnot. It can accommodate a lot of use cases, And all of that was developed by large communities over many years. And that sort of justify why it makes sense to capitalize on that instead of developing something from scratch because of that large and active communities. And to put things in a bit more context, in that specific scenario, the building block, for example, you acquire data from like some hardware, scanner, MRI, and whatnot. And then you have your application that provides some modules. On top of that, you have a broad collection of extensions that specialize the functionality. And then, for example, if you wanted to do some real-time guidance, you have to integrate even more hardware, which was some scan navigation system probe into your system. And redeveloping that from scratch would be time consuming, and capitalizing on the desktop application is sensible in that scenario. And I mentioned earlier that it's important that your desktop application already work with Python. In the case of a desktop application, we have an embedded Python interpreter that allows us to interact in real time with all the objects that are loaded in the application, load new objects. And it also means that all the functionality are wrapped in Python and made available. And the SlicerJupyter kernel tap into that and leverage that. And they're going to see how in a few minutes. To summarize, yeah, we can install any Python package inside the Slicer Python environment. It means any wheels that are available on SciPy can be installed. It's integrated by taking control by it's a Qt application, and then the evaluation of the Python statement is done through the Qt event loop. And then, what is the traditional Jupyter kernel? You have the Python interpreter, you have IPython Jupyter kernel, and then you have like a web application called the Jupyter Notebook Server. You have the Jupyter Notebook Server which orchestrates everything, that provide a web page, and then the Jupyter Notebook Server start a specific kernel and establish your communication, and then from your web page you can evaluate Python statement and get the output. But then in the case of the desktop application, you have an embedded Python interpreter. And now how do we bridge the two? It means instead of starting a regular Python interpreter, we have a new kernel that's made available, and that's the Slicer application in itself gonna act as a kernel. And the small layer provided by the extension is in charge of fulfilling the contract to communicate with the Jupyter Notebook Server. And then there is multiple levels of interactivity that are offered. There's 4 of them. The first one is you want to see the state of the view and after loading data. And you want to simply, for example, update the slider, and then when you release the slider, you pull the state of the view. And that's what we call the level 1 of interactivity. That can be done for 2D view or 3D view or any other view in the application. Then level 2 is you want to capture, you want to have some higher level of refresh, and that can be done through a small like module we expose called Slicer Notebook, and then we can also combine these different views into layout. And similarly to the previous level, you can update the state of any view. Then the level 3, we're gonna start to capture the mouse events on the web page and propagate them down the pipe all the way to the application. And you can update the 3D view, rotate, or interact with the 2D view by adjusting the window level or the slides that being viewed without having to have a specific like Jupyter widgets. And then the 4th level of integration will be to display the complete application and not just like a specific view. And we can do it by displaying the full viewport of all the existing layout, or displaying the complete application on the right side. And that's like the traditional Qt application that's displayed directly in the notebook, and you can interact with that application. And in that specific case, the application is aware that it's connected to a kernel. And then on the bottom right, you can see that application is managed by Jupyter. And that's the gist of the integration. Another neat feature is that if you have like special sort of special object like model, transform, tables, list of markup, there's a way to expand the capabilities of Jupyter to display this, to provide a rich support for this object and display them in the output cell of your Jupyter notebook. And overall, what motivated that is to improve the tutorial experience and also streamline the testing of this tutorial, and avoid having, for example, to switch between like a PDF and the application, and you can have like running side by side. You can see the application if you run all of that locally, and then just go through each cell and see the application updated in real time. And yeah, we're gonna try a small demo just to illustrate. And I already started the demo earlier, that we are like loading through a MapBinder, which is a platform to run notebook in the cloud for you. And here, of course, it has to restart the kernel. And in the meantime, I can open for question and look like. Okay, the kernel in the cloud is restarting because it timed out. And while that is happening, let's go back to the slide. And what's next? Yeah, that was made possible through collaboration with multiple people over a few years. And they are all acknowledged here. And yeah, then there's a link to the actual documentation. And then a previous blog we wrote with additional details. And just gonna open the link again. And this service is provided for free, and sometimes it's time out. But in the meantime, is there any question?
Questions, anyone? I don't see anything in the chat. Oh, is it coming up here?
I have a question. So this is an example of a C++ application with Python wrapping working in Jupyter notebooks.
Yep.
Once you have the Python wrappings, what would you say is the amount of effort required to get it to work in Python and Jupyter notebooks?
Now we have like two working use cases. We have done a similar implementation for ParaView, and we have the one for Slicer. To have an initial prototype, like few days of work to get something going. But then like Davis is in the details, and to which level the current wrapping is done. Is it? Yeah, there's some details to review, but to get I think a basic integration, like few days of work. Yeah, I have the demo working, and I'm gonna run through the cell, and I'm just executing the different cell here. We just display one of the slice viewer. And the interesting part going to be the interactive one, the dynamic view. And now here, and now if I update, you can see that the view are updated. This one, And same thing here, we're changing the cropping of the volume rendering, and we can see the view is updating, we can rotate. Then we have level 2. And yeah, we can also update the view. And interestingly, all of that is running in the cloud on some like random instance started and provided by my binder. You will get faster refresh rate if you deploy the server in-house, and you will reduce the latency. And now the interactive widget where we can use the mouse. Also, the demo effect is not working the way I would like to.
You might be straining your bandwidth a little bit.
Yeah. I mean, it's more like what's happening in the cloud, and it's independent. Like the data that are sent back to the client are fairly small.
Oh, okay.
Yeah, this is just like a simple like image that's sent back. It means it's more like tapping into that free service and not deploying like on your own premise. That's more like the issue.
So if somebody who wants to use it would spin up their own instance to use, or is there a public service?
I mean, this is a public service, my binder, but this is completely free, and it's just for like sort of demo purpose. If you want to, let's say, host like we have some collaborator who are organizing tutorial with like 50 or 100 students. What's going to happen is that they're going to provision like Amazon instance that they control and deploy on the Amazon instance, or host that in their internal cluster, and then have the student start session and follow like tutorial and learning classes. Okay, and here we can see I can interact with the view. Yeah, I can change the slice or zoom. If I use the keyboard, I can go like the slice. And then the interesting one is the last level where we will see the entire application. And here it starts like a VNC session. It's using HTML VNC, and I can interact with the application over the wire. And it's like that. And now, if you want to switch in full sees the complete application, we can call the set content to full, and it's going to update the view we saw above. And here we have like access to the full application that you will get on the desktop through that JavaScript VNC, if you will. And you could also look at that through a tab. And here we have like the application running in a tab that's managed by like that random cloud instance that was started by my binder. And yeah, and here are some examples of like rich display. But yeah, that's it for my part.
Great. We can take some questions in the chat.
Stop sharing. Oh.
So yeah, these are all great examples. So it seems like all these tools are interfacing with each other, Trame and VTKGAS and TK widgets, and even Slicer with SlicerJupyter. How would you advise somebody who wants to deploy an app to choose which tools to use, even of these sets? Because some of them are a little bit like there's some overlap
And there's some, of course, advantages and disadvantages to each.
Looking at the goal, what's the goal, and that will help answer the question. Is it like a short-term lived demo? What's the amount of funding to maintain like cloud instance over time? How many users? What's the vision long-term to transition to like a full web stack or to expose an existing application? It really depends on what's the use case and what's the goal. Like all these tools are like relevant for very specific use case, and understanding what use case will help understand the question, answer the question, I think.
Yeah, I will take another stab at it also, but I agree with Jesse. It really depends, and that's the trickiness with web in general, is what is the right answer, but it really depends on the questions. Tools like VolView or ITK widgets are like more on the edge of an application that can be extended to do something. Trame is coming from the other world where it's a library and you do whatever you want. But we give you like connections to ease the usage of VTK, Purview, Plotly, whatever, or integrate something else. And Slicer is like Jesse presented, like an open source application that has been developed and built upon like hardware, infrastructure, libraries, and stuff like that. So that's where also it makes sense to try to expand those initial capabilities. And there's lesson learned on every of those projects that if you come to ask the questions, okay, this is my problem, what is the best answer? Then we can pick and choose and say, well, that's probably the best path for you. That is like in between maybe those 4 things or something like that. If that makes sense, hopefully.
Yeah, I think so. So Trame is, on the customizable end, and you said ITK widgets is more application driven, or is that did I understand that correctly?
Well, from my point of view, I was like thinking VolView is definitely the end application. ITK widget is like close to that to some extent because it has already some UI and so on, but it also like starts stepping towards like the customizations or the customability. So you can easily drop something that has lots of features and capability without you adding any burden on your side to do those things. While in Trame, you will have to say, well, I want a button or I want a slider or something like that. But I don't know, JC, maybe you have a better point of view on some of that.
Yeah, and also like some of them are like client side and don't require a server. Some other one require a server, and also depend where are your data located. Can you like it's also specific on the type of data you have to deal with, and yeah, and number of users, because like, for example, when you have the server, then you have to maintain this session. If you have thousands of users, that can scale, but then the cost of maintaining this like cloud instance and then load balancing, and then do you want access like across East Coast, West Coast, the entire world? I mean, all these questions need to be like considered in this scenario, I think.
Thank you. Any other questions? Jack?
These tools all seem like really interconnected, right? They all are using ITK widgets and whatnot. Do you have any suggestions for a software developer for how to develop architecture that is scalable in this way, where you can like reuse components and things like that? Any like little tips or whatnot?
Yeah, I think one of the first thing is like one of the common building block is like at the end there's VTK modules or ITK modules, depending if you're depending what are the existing foundation in your application, and then sort of like modularizing to have components that can be reused, and then you can play Lego in some way, and then sort of move forward with any of these approach, because some of them you may down the road leverage WebAssembly and then build this component for the web or not. In that case, you can just compile like down to C++. And then have leverage the wrapping of VTK, expose that, and then in no time you can create an application with Trame. It means, I think, modularizing and thinking on terms of reusability will be the first thing I would say.
Cool. Yeah, and then just to follow up about WebAssembly, to me that's pretty new technology. How have you guys found WebAssembly? Is it painful? Is it good to work with?
every approach got their pain points. When if you go down the road of like solving an actual problem, it means and we have like experience with WebAssembly for the past. We started like back in 2015, if not earlier, to dabble with like Emscripten, and now we are working with Wasm, Wazi, and whatnot, and we are like sort of making progress on all of this front.
I guess it really depends on your background. If you're a C++ developer and you have no clue what web is, you could say, well, WASM is probably the best approach to get your feet wet there. If you're more like Python world and you're happy with a server, maybe using VTK with either remote rendering or local rendering with Tram, I mean, because we've got those building blocks or those Lego that JC is kind of talking about. You don't need to know too much about it, and then you get something running very quickly and with very good performances. So
Yeah, makes sense. Thanks.
it depends.
And also where it sort of makes sense, like when we deal with IO, re-implementing IO from scratch, I mean, for like the basic use case, easy. That could be done in one afternoon. But there's like decade of like bug fixing to address corner case. It means that's why often transpiling existing code base to deal with the IO for reading like all this file format makes sense, because it's very easy to introduce, like to miss things when you have to deal with like corner case and whatnot for like reading and writing files.
All right. Thank you. One more round of applause. That was fantastic. And I think we're out of questions and out of time. So thanks.
Thank you very much.
Well, thank you, everyone.
Thank you all.